A rocket engine is asked to do something close to impossible, and to do it without braking, for minutes at a time. It has to take tons of liquid fuel and oxygen, burn them into a fire hotter than parts of the sun, and aim that fire through a nozzle to lift a skyscraper off the ground. The way it lifts anything is almost insultingly simple to state. You throw mass backwards fast, and the machine is pushed forwards. The more mass you throw each second, and the faster you throw it, that is your thrust. So a powerful engine is really just a machine for moving an enormous river of propellant every single second and hurling it out the back. SpaceX's Raptor pushes roughly 650 kilograms of propellant through itself per second. That is most of a small car, turned to fire and thrown out of a nozzle every second. The whole difficulty of building a rocket engine hides inside that one sentence. How do you feed a fire that hungry? Here is the trap. The fire burns inside a chamber that is already at crushing pressure. To push more propellant into it, your pumps have to raise that propellant to a pressure even higher than the chamber. We are talking about pumps powerful enough to drain a swimming pool in seconds, against a back pressure hundreds of times stronger than the air around you. Pumps that strong need an engine of their own to spin them. So inside every big rocket engine, there is a second, smaller engine, a turbine, whose only job is to drive the pumps. And a turbine needs hot, high-pressure gas to spin. So you have to burn a little propellant just to power the pumps that feed the propellant to the main fire. How you feed that inner turbine is called the engine's power cycle. It sounds like a detail. It is actually the whole game. The simplest answer is the open cycle, also called the gas generator cycle. You burn a small side stream of fuel and oxygen in a little chamber, use that hot gas to spin the turbine, and then, when it has done its job, you just throw it away. You dump it overboard. You have seen this without knowing it. On engines like the old Saturn V F1 or SpaceX's own Merlin, there is a second, sooty exhaust venting off to the side. That is the gas generator, breathing out propellant that will never become thrust. It is simple, it is reliable, and it works. But every gram you burn to run the pumps and then throw away is a gram that did not help push you to space. You are quietly leaking performance out the side the entire flight. So engineers asked the obvious question, what if you did not throw that gas away? What if, after it spins the turbine, you routed it back into the main chamber and burned it for thrust too? Now nothing is wasted. That is staged combustion, a closed cycle, and it is how the most powerful engines in history have worked, from the Soviet RD-180 to the Space Shuttle's main engines. It is more efficient, but it hides a knife. In a normal staged combustion engine, one spinning shaft can carry a pump for fuel on one end and a turbine driven by oxygen-rich gas on the other. Fuel and hot oxygen on the same shaft, separated by one thin seal. If that seal ever fails, fuel meets hot oxygen in exactly the place you least want it, and the engine can tear itself apart. For decades, that single seal was one of the most feared parts in all of rocketry. Before we fix that seal, look at what Raptor chooses to burn, because it is part of the same story. Raptor runs on methane and liquid oxygen, methalox. Most rockets before it burned either kerosene or hydrogen. Methane is a deliberate choice. It burns clean, with almost none of the soot that kerosene bakes onto the inside of an engine, and that matters enormously if you want to land the engine and fly it again the next day without taking it apart. It is denser and far easier to handle than hydrogen. It is cheap, and there is one more reason, the one that gives this project its name. Methane is the one fuel you could actually manufacture on Mars, out of the carbon dioxide in the air and water from the ground. An engine that runs on methane is an engine that could, one day, refuel itself on another planet. Now, the seal. The fix is an idea so demanding that for half a century, almost no one could turn it into a working flight engine. It is called full-flow staged combustion. In an ordinary engine, there is one preburner. Full-flow uses two. One preburner runs oxygen-rich and is fed all of the oxygen. The other runs fuel-rich and is fed all of the fuel. Every last bit of both propellants passes through its own preburner and its own turbine before reaching the main chamber. Nothing takes a side path. Everything flows through. That is what full flow means. Let us walk it through. Follow the oxygen first. All of it goes into the oxygen-rich preburner, is partly burned into hot gas, and that gas spins the oxygen turbopump before pouring into the main chamber. Now follow the methane. All of it goes into the fuel-rich preburner, becomes hot gas, spins the methane turbopump, and pours into the chamber too. So by the time the two streams meet, they are not cold liquids anymore. They are both hot gas. In the main chamber, gas meets gas. And because each shaft now only ever touches one propellant, the fuel pump and fuel turbine on one side, the oxygen pump and oxygen turbine on the other, that terrifying seal between fuel and hot oxygen simply does not exist anymore. There is nothing there to fail. That single architectural choice pays off 3 times over. First, because all of the propellant flows through the turbines instead of a small side stream, the turbines can make their power while running cooler. A cooler turbine is a turbine that does not wear out, and an engine that does not wear out is an engine you can fly again and again. Second, gas meeting gas in the chamber mixes far more completely than liquid sprays, so the burn is more stable and more complete. Third, you have deleted the most dangerous seal in the engine. None of this is free. You are now balancing 2 preburners and 2 turbopumps that have to stay in perfect agreement, at pressures that punish every material you build them from. This is why full-flow staged combustion was, for so long, the engine everyone admired on paper, and almost no one finished. There is one number where Raptor stands alone, and it is the one that matters most: chamber pressure. The harder you can squeeze the fire inside the chamber, the more thrust you get from an engine of a given size, and the more efficient it becomes. Raptor 2 runs at around 300 bar. That is 300 times the pressure of the atmosphere around you, held steady inside a chamber wrapped around an explosion. Raptor 3 is pushing toward 350. No flight engine in history has ever run at a higher chamber pressure. This is the headline, the place where the full flow cycle and years of brutal engineering turn into a record that nobody else holds. Step back and look at the company Raptor keeps, because it is almost empty. Full-flow staged combustion has been attempted only a handful of times in the entire history of rocketry. The Soviet Union built the RD-270 in the 1960s. The United States built a test article called the Integrated Powerhead Demonstrator in the 2000s. Both ran only on test stands. Neither ever flew. Raptor is the 3rd full-flow staged combustion engine ever built, and the first one in history to actually fly. Then SpaceX did the thing that is arguably harder than building one at all. They put it into mass production. The Super Heavy booster does not fly with one of these engines. It flies with 33 of them, clustered together, lighting at once. So why pour all of this difficulty into a single engine? Because the engine was the bottleneck. For the whole space age, Rockets were thrown away after one flight, mostly because the engines could not survive being reused cheaply. An engine that burns clean, runs its turbines cool, deletes its most dangerous failure mode, and can be built by the 100 changes that equation. Raptor is not just the most advanced rocket engine ever flown. It is a bet that the hardest machine to build can also become the most ordinary, something you stamp out, fly, land, and fly again, and one day fuel from the soil of another planet. The rocket was never really the hard part. The engine was, and for the first time, the engine is starting to look solved.